Hello everyone, wishing you all a very good morning. Am I audible and visible to all of you? Good morning, Deepak. Good morning, everyone in the class. Well, in yesterday's class, we had discussed what is force and what is work done by the force. Force is a push or a pull. It either changes the size or shape, or it changes the state of rest or state of motion. Changing size and shape will be coming in forthcoming chapters. Right now, we are concerned about what force is doing to change the state of rest or the state of motion. So when force changes the state of rest or the state of motion, the body is moving. And when the body is moving, we have seen the work done by force. Work done by force is the integral of F dot ds. The last point that we discussed in the last class was work done by a constant force, and we derived the formula for work done by a constant force. In your notes, it is given in this fashion. The way we have written it is work done by a constant force delta W is equal to F dot delta R, where F is the constant force and delta R is the displacement of the body. Do we understand this? Can I have some raise hand that we understand this, sir? Okay. Now, this F dot delta R, we have also seen can be written as magnitude of F into magnitude of delta R multiplied by cos theta, where theta is the angle between force and displacement. Theta is the angle between force and displacement. So work done is positive or negative. It depends on the value of theta. If theta is acute, work done is positive. If theta is obtuse, work done is negative. And if theta is 90 degrees, work done is 0. We have seen that. Now, in this small node that you can see, we can also write this F into delta R into cos theta in this fashion. I can write this work done as F cos theta multiplied by delta R. Now, when I look at this component of F cos theta, as you can see in this figure, which I'm going to enhance for you, and you are supposed to draw this figure. Now, see this figure and see what I have written. In this figure, if you can see, let me make it bigger. I think this is good enough. Okay. In this figure, as you can see right now, what we have done, we have a block which is kept on a surface, and this block is displaced from point number A1 to point number 2. Point number 1 is the initial position. Point number 2 is the final position. The displacement is given as S vector. I can write it as delta R vector, change in position vector. As you can see, the force is applied in a different direction, which is not in the direction of the displacement. It is at an angle, and the angle is acute. This is the angle theta. Now, by vectors, we know that this force can be resolved into two components. One component will be F cos theta, and the other component will be F sin theta. Now, once you resolve a vector into two components, you actually don't need that force because that has already been resolved. Now, this force can be thought of as two different forces. One is F cos theta, which is along the surface. The other one is F sin theta, which is perpendicular to the surface. Now, if someone asks me what is the work done by these two forces, if you can find the work done by these two forces and add them, we will get the work done by the force F, which was the original force. So this is another way of understanding the same thing. Now, if we have to find out the work done by this F sin theta valley force, now look at this F sin theta valley force, which is perpendicular, and the displacement is horizontal. If you look at this case, the angle between this force F sin theta and displacement is 90, and hence work done by this component or this force is 0. Do we understand this? Can I have some raise hands? So the work done by the perpendicular component of force is 0. The only work that any force can do will be in that component, which component is in the direction of displacement. Only that force will do work which is in the direction of displacement. If force is not in the direction of displacement, we will have to find the component of the force which is in the direction of displacement. In this case, the component of force which is in the direction of displacement is F cos theta. Now, F cos theta is in the direction of displacement. What is the work done by this force? This is the constant force, F cos theta multiplied by displacement, because angle is zero because they are in the same direction, and hence you can get the answer as F cos theta multiplied by delta R. So there are two ways of understanding work done by a constant force. One way, you can find out the dot product F dot delta R. Again, it will be equal to F into delta R into cos theta. Or the second way is you can resolve the force into two components, one perpendicular, other parallel. The perpendicular component work done will be zero. Only the parallel component will do any work. And this is how you can understand this. I hope you have noted this down. Yes or no? Please note this down. Draw this diagram so that we understand this work done in two different ways. We have understood this work in two different ways. Two different ways we have understood this work done. So you can understand it in one way or you can understand it in second way. Both are similar, doesn't make any difference. So that is the first thing that you must understand. The second thing, so you can write important notes, star important notes, and this is the first point of that star note. If you have, instead of one force, if you have two or three or four forces, what is the work done by all these forces? So if a number of forces F1, F2, F3, Fn are acting on a body and shifts the body from initial position vector R1 to final position vector R2, then work done, I have written work done as delta W. So work done delta W will be the net force F1 plus F2 plus F3 and so on. Beach may have dot product. You can see the dot product in between. Dot R2 minus R1. Remember, R2 minus R1 is the change in position vector, and change in position vector is simply displacement vector. Do we understand this? I hope everyone understands this. The only difference we have done here is instead of one force, we have more than one force, and we are supposed to find out what? We are supposed to find out the displacement of the particle first. You will have the initial position vector. You will have the final position vector. You have to find out the displacement vector. Once you get the displacement vector, you dot the force with the displacement vector and you will get the work done by this complete thing. I hope everything is clear. Let us now move to a question that we can solve on this concept. Question number one. One force F1, which is equal to 2I minus 3J plus 4K. I'm just giving two forces. I'm just not wanting to complicate things. F2 is minus I minus 2J plus 3K shifts a body from the first point is 2, 1, 3 to the second point is 3, 2, minus 1. Find number 1, work done by force F1. Number 2, work done by force F2. Number 3, total work done. Total work done means work done by all the forces combined, your time, starts now. First force is 2i minus 3j plus 4k. The second force is minus I minus 2j plus 3k. The particle is shifted from 2, 1, 3 to 3, 2, minus 1. To find out the work done by all of these forces, F1, F2, and then you have to find out the total work done. I hope the question is clear to all. In the online class, Karthik, Charita, Deepak, Shreya, I hope all of you are trying the question. I hope all of you have tried this question. So the first step is finding out the displacement vector. How do you find the displacement vector? From the final position vector, you have to subtract the initial position vector. That means you have to subtract 2 from 3. 2 is the initial, 3 is the final. 1 from 2 and 3 from minus 1, and put I, j, and k. I hope you remember this. So 3 minus 2 is 1, 1i. 2 minus 1 is also 1. So 1j. Minus 1 minus 3 is minus 4k, and hence the displacement becomes I plus j minus 4k. Did we all get this answer? Yes or no? Can I have some raise hand? We got this answer for the displacement. Great. This is the displacement. Now you can go ahead and find the work done by the force F1. I will write it as work done by 1. Work done by 1 will be F1 dot with displacement. F1 is 2i minus 3j plus 4k. It has to be dotted. It has to be dotted with I plus j minus 4k. You know how to find the dot product. We'll just write the answer. 2 I dot I will be 2. Rest will be 0. Minus 3j dot j will be minus 3. So 2 minus 3. 4k dot with minus 4k will be plus 16, and your answer will be 15 units. I don't know the units of force. It is not given. So it will be work done by force 1 is 15 units. Do we all get this? Can I understand? Can I have some raise hand that we got this? How I got this? I just took the dot product of this F1, which is here, with this displacement delta R, which is, oops, here, green, 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 green. Now, if we have done this, we will now move on to find the work done by the force F2. How will I get the work done by the force F2? Work done by the force F2. I have to take the force F2, which is here. So I'm just taking it, minus I minus 2j plus 3k, and I have to dot it. Anyone having any doubt?
Yes, sir.
Yes.
Minus 16, sir.
Oh, yes. I made a mistake. Sorry. Mistake. Minus 16. So the answer will be minus 17, correct? Oops. Sorry, I did a mistake. So the answer will be minus 7. Is it correct now? Okay. Work done by the second force is minus I minus 2j plus 3k. And I have to dot it with this R. And R is I plus j minus 4k. So it is I plus j minus 4k. So I just take the dot product minus I dot plus I is minus 1. Hope I am not making a mistake this time. Minus 2j dot with j is minus 2. Again plus minus की mistake nahi. 3k dot with minus 4k is minus 12. So I will get minus 15 units here. Do we all understand this? The pink one. Minus 15 units. All of you got the same answer? Yes or no? Now, we have to find the total work done. We can apply the formula F1 plus F2 dot with that thing. But instead of doing that, we can do it in many ways. We can first find the value of F1 and F2 and then take the dot product with displacement. Or since we have found out the work done by the two forces, first work done is minus 17, second work done is minus 15. I don't have to take the dot product again. I can simply add the two works and I will get the total work. So total work will be minus 17 minus 15. That will be equal to minus 32 units. That would be the answer. If you don't want to do it this way, you can add force F1 and F2 and take the dot product. Any ways you do it, you will end up with the same answer. Am I clear? Do I have an understanding? Please raise your hands and let me know. Okay, everyone in the class, everyone in the online class. Shreya, Charita, Deepak, are we there on the same page? Okay. If we have understood this, it's a very good thing that we have understood this. Now, what we are going to do, go back and understand the next thing. Please note the question down till the time that we are moving back and we are back to this screen. Now, we have also seen when is the work done positive, when is the work done negative. Here it is a small table given that will tell us when is the work done positive and when is the work done negative. So if you understand this, you don't have to draw this. If you don't understand this, you can draw this table which is telling us when is the work done positive. As you can see in this case, here you have force going in one direction and displacement is in this direction. But when I resolve this force, I will have one component parallel. So if one component is parallel to displacement, that means the angle is acute. Angle is acute. In this case, I will have positive work done. Positive work signifies that the external force favors the motion of the body. It basically means that external force is making the body to move in the same direction. Whenever there is friction, normally it should always be opposite to motion. So friction work done is going to come negative in some cases, not in all cases, we will see that. But if you have a component of force which is parallel to displacement, work done would be positive. Now, what are the examples and when will the work done be negative? If you just take the reverse case, what do you mean by the reverse case? By reverse case, we mean the force. Oops. By reverse case, we mean force is like this. Displacement is in this direction. As you can see, the angle is obtuse. When the angle is obtuse, if you resolve the force, one component will come like this and the other component will come like this. This component does not do any work. This component will only do work. It will be equal to f cos theta, but f cos theta now is in the reverse direction and displacement is in the forward direction. Angle becomes 180, cos of 180 is -1, and hence we will get minus work. It is simplified in this fashion. Uh, if you can see here, you have obtuse angle. If you see here, you have acute angle. Do we understand this? So if the angle is acute, work done would be positive. If the angle is obtuse, work done would be negative. If you understand this, no need to write this. But if you can write this, it is good to have it in a tabular form. Here are some examples of positive and negative work. As you can see, when a person is lifting a body from ground, if you have gone to gym or if you have seen people doing this gym, when they are lifting the weight up, force of the man is upwards and he is trying to lift it upwards. Displacement is also upwards, and hence work done by this man, force applied by this man is positive. Work done by this man is positive. But if I look at the second case, in the second case also, man is lifting the weight, but right now they are thinking about work done by gravity, force of gravity, the weight of this block is downwards, displacement is upwards, and in this case, work done by gravity is negative. So in one case, work done is positive, work done by man is positive. In second case, work done by gravity is negative. Positive work, negative work. Positive work, negative work. You have any doubt, please ask.
Sir,
Yes.
sir, can you please show previous screen once?
Okay. So this is how we can understand the concept of positive and negative work when the angle between force and displacement is acute, work done is positive. If the angle is obtuse, work done is going to be negative. And we have seen the example. We have seen the example of a man lifting a block or a weight. Work done by man is positive, but work done by gravity is negative. Have we done this? This is there already in your notes. So if you miss something, you can always write it from the notes that are already there in with you in soft copies. That is the example of positive and negative work. We have already discussed this. I hope you have written this. Can you move forward now? Okay, note it down. Okay. Then the next point that you can see is this one. When do we have maximum work done by a force? When do we have maximum work done by a force? Now, maximum work done by any force is F multiplied by delta R, where the value of cos theta is maximum. And the maximum value of cos theta is 1, which happens at theta is equal to 0 degree. That means if you want any force to do maximum work, if you want any force to do maximum work, the angle between force and displacement must be 0. So if you have to move a block, this is a block of mass m, and you are applying a force, and you want maximum work to be done by this force, that force should be applied in the direction of displacement. If the displacement is in the forward direction, as in this case, the angle between force vector and displacement vector must be 0, and then you will have maximum work done. If you want the work done to be minimum, by minimum, I mean it is negative maximum. So it's better to call it negative maximum than minimum. The minimum work will be minus F into dr, and that will happen when the value of cos theta is minimum or maximum on the negative side, minus 1, or theta is 180 degrees. That means if this is the surface, I want minimum work, for example, then if I apply force like this, the displacement should be in the reverse direction. Now you will say, sir, how will this happen? That force is applied in the forward direction and the body is moving in the reverse direction. There are many examples that you can think of. You can think of this force as frictional force. The body is moving forward, frictional force will be backwards, work done will be negative, and it will always be maximum because the angle between force and displacement will always be 180 degrees. Do we understand this? Yes or no? Can I have some raised hands? Please note this down so that we can move further ahead. I hope you have written this. Can I move forward now? Hope everyone has done this. This is the next concept. We have seen when is the work done by force negative. Now we are elaborating on the three different cases in which the work done by force is negative. We remember work done delta W if F into delta R into cos theta. I will write it in my way. Delta W is F into delta R into cos theta. Now I want this work done to be zero. Now, if any of these three quantities, f or delta r or theta, cos theta is zero, then my work done will be zero. In the first case, what we have done, if the force is perpendicular to the displacement, as I said, work done in physics is different from work done in real life. This is a hard-working porter, coolie, we call them in Hindi. When he's lifting a heavy load on the top of his head and he's moving on horizontal road, physics is sometimes funny. In physics, the work done by him or by gravity on him is zero because displacement is in the horizontal direction and the weight of this luggage is downwards. So work done by luggage or gravity or this person is zero because he is applying force in the upward direction, but he is moving in the forward direction. Angle is zero. Work done by this porter in physics is zero because the angle between force and displacement is zero. Angle between force and displacement is 90 degrees. That is the first example. In second example, when a body moves in a circle, work done by centripetal force is zero. I hope that you are studying circular motion. I do not know whether you have understood centripetal force, but you must have understood that there is an acceleration which is known as centripetal acceleration, which is towards the center. Have you read centripetal acceleration? Yes or no? Please raise your hands. Yes, so you must be knowing that centripetal acceleration is towards the center and body is moving along the tangent. The angle between centripetal acceleration and velocity is 90 degrees. Now, centripetal acceleration is caused by centripetal force. Wherever you have an acceleration, there must be a force. Force can only produce acceleration. Centripetal acceleration is produced by centripetal force. Centripetal acceleration and velocity, the direction of motion is perpendicular and hence work done by centripetal force is also zero. That is the second example. The third example you don't know because that will come in your 12th standard. So we'll discuss it here. So you can take this example out, but write the other two examples. Work done by this force is zero because angle between force and displacement is 90 degrees. Do I have some raised hand that we understand this? Great. Please note it down so that we can move on to the second case and the third case, which are pretty damn simple. First, you note down these cases, then we'll move on to the other two cases. So in the first case, we have seen work done by force is zero if the angle between force and displacement is 90 or force is perpendicular to displacement. Two examples, coolie or a porter keeping luggage on his head and moving, work done by him is zero. Sounds funny. It is funny, but in physics it is zero. That is why I said work done is different in physics as to what we do in daily life right now. In physics, I am hardly doing any work because there is no force and I am not moving. There is force, gravity is there, but I am not doing any work. But I am losing a lot of energy. I am losing a lot of energy. But in physics, it is not work done. Okay. Then what are the other two cases? The other two cases are pretty damn simple. If there is no displacement, work done is not zero. This gentleman, this boy is trying to push a heavy stone and the stone does not move. He is losing a lot of energy. Yes. In day-to-day life, he is doing work. But in physics, the work done is 0 because there is no displacement. Number 3, if there is no force, obviously there is no work. So if F is 0, displacement is 0, work done is definitely 0. Please note it down. Simple facts. We are discussing work done by a constant force. Now, even if it is not a constant force, even if it is a variable force, remember centripetal force, centripetal force, centripetal acceleration, centripetal acceleration, which is towards the center. Can you tell me, is centripetal acceleration constant or is it a variable? Anyone in the class? Centripetal acceleration, is it a constant acceleration or it is a variable acceleration? Who will tell me? Anyone? You have already read centripetal acceleration and tangential acceleration. Can you tell me centripetal acceleration in uniform circular motion, is it constant or is it variable? No one knows it?
Constant, sir.
It is constant. What makes you think that? What is your name, beta? Wow. If you say something, please tell me your name so that I can recognize you. Yes, beta. What's your name?
Surendranath, sir.
Rangnath. Centripetal acceleration is constant. What makes you? What is the value of centripetal acceleration? What is the value of centripetal acceleration? Anyone? Rangnath says that centripetal acceleration is constant. Okay, I understand it. What is the value of centripetal acceleration? Can anyone tell me that? Online class, offline class, anyone? You have done centripetal acceleration or not? If you have not done it, not a problem. Have you done centripetal acceleration? Yes, beta?
Sir, centripetal acceleration is 0, sir.
A body is moving in a circular path with a constant angular velocity, a constant speed.
Sir, but it has 0 displacement, sir.
I don't understand. Let me put the question in a different way, probably. Maybe I'm confusing the question. Let me put it in a different way. Just wait. Just wait. Have you done centripetal acceleration or not? Please answer this question first. Have you done centripetal acceleration? Study centripetal acceleration, yes or no? If you have not done it, not a problem. Have you done centripetal acceleration? Yes, no is a simple answer. It's a binary thing. Either you have done it or you have not done it. Simple. No answers? No answer is a very, very horrifying answer. No answers are right or wrong. I'm not worried about right or wrong answer, but no answer is a horrifying way of replying.
Sir,
Yes.
we have not done centripetal force.
Okay. So that's an answer. Okay. But you have started circular motion, right? Yes or no? You started circular motion. Am I correct? Or am I wrong here also? Okay, this is my circle. I hope you understand this. Are you doing circular motion with the other sir or not? I'm having the notion that you are studying circular motion. I might be right, I might be wrong. You're not doing circular motion? Okay. Okay, if you're not doing circular motion, let us not discuss this. Okay, but I just give you a brief idea. In circular motion, the particle moves like this. The particle moves like this. And if the speed is constant, here v speed, it is known as uniform circular motion. Now in this circular motion, what we have is we have an acceleration which is always pointing towards the center. We have an acceleration which is always pointing towards the center, and that is known as centripetal acceleration. Now this centripetal acceleration in case of uniform circular motion, since it is towards the center, it is known as centripetal. Centripetal means seeking center, towards center. It's always toward the center of the circle. Now, the centripetal acceleration, if I talk about the magnitude of this centripetal acceleration, it is equal to omega square multiplied by r, where omega is the angular velocity and r is the radius of the circle. Or I can write it as v squared by r, where v is the speed of the particle with which it is moving. Now the centripetal acceleration, as you can see, it is constant, but it is constant only in magnitude. It is constant in magnitude. The magnitude remains same. The magnitude remains same, but as you can see, the magnitude is same, but you can see that the direction continuously changes. Direction changes. And hence, since it is a vector and its direction changes, therefore centripetal acceleration is non-uniform acceleration. Do we understand this now? It is non-uniform acceleration because even though the magnitude remains constant, the direction of this acceleration changes. Can I have some raised hand that we understand this? You may not know the meaning of centripetal acceleration. I have just shown you that this acceleration is towards the center. It has a constant value, but the direction keeps on changing always. The direction keeps on changing always. The direction keeps on changing always. So in this case, also, when the direction of this acceleration changes, it is a non-uniform acceleration. Every acceleration is produced by a force. So it is produced by a non-uniform force. Because the force is changing direction, even then, the angle between force and displacement always remains 90 degrees. And hence, work done by this force, which is causing centripetal acceleration, is zero. Please remember that. So if the angle is 90, the work done has to be zero. No matter the force is constant or the force is variable. Do I have understanding of this? Can I have some reason that we understand this? Okay, now there are some sample problems taken from your notes. We will do problem number 1, 2, and 3. And the rest of the problems you will have to do on your own. That will be your task for the day. Problem number 1 is what we are going to do now. It's a simple problem. It came in the engineering exam way back. Now, whatever problems have come way back in an engineering exam, in today's case, they are considered to be difficult and they are likely to come in your JEE Main. So, this question has come in JEE Mains as well, I think in the year 2017 or something. Not the same values, obviously, but the same concept. The question is pretty damn simple. A body of mass 5 kg is placed at the origin and can move only on the x-axis. A force of 10 Newton is acting at a direction making an angle of 60 degrees with the x-axis and displaces it along the x-axis by 4 meters. What is the work done by this force? The time starts now. Simple question. Should be done simply. What is the work done by this force? Force is 10 Newton. Mass of the block, I don't think it is required. Force is 10 Newton. Angle is 60 degrees. It displaces it around 4 meters. It should get displaced in the same direction because it is not moving. Force is only moving it. That means force. The displacement is 4 meters. Angle is 60 degrees. How will you find this? How will you solve this? I hope you can do this. Yes or no? So how do you do this? Work done by force is F dot delta R. It is F into delta R into cos theta. F is 10, delta R, displacement is 4, cos of 60 is half, and you get the answer as 20 joules. SI unit of work done is joules or Newton meter. Do we all get the answer? Can I have some raised hand that we understand this? Boys, are we there in the class? Left hand side benches. Are we doing the question, boys? Okay. Then we move on to problem number 2. Problem number 2 is also a very simple problem. Force is given as 5I plus 3J is applied over a particle which displaces it from origin. So the initial position is origin to the point. The second position is 2I minus 1J. Instead of writing 1J, it can be done as J. 2I minus J meters. What is the work done on the particle? So force is given in vector form. You have to find the work done by this force. The baton passes on to you. What is the answer for this one? So how do you do this? Problem number 2 is very simple. You just have to find out the dot product of force with displacement. Force is 3I plus 5I plus 3J. You have to dot it with displacement. How do you find the displacement? Final position vector is given to you, 2I minus 1J. Initial position is 0, origin. So final minus initial will be same as the final. 2I minus J. You take the dot product, you get the answer, and you stay happy always. Did we get this question? Can I have some raise hand that we got this? Everyone, boys, are you sleeping? Only first bench boys are there. Yes, second and third bench are also waking up. Problem number 3 is the next one in line. Please do it. Problem number 3. A horizontal force of 5 Newton is required to maintain a velocity of 2 meter per second for a block of 10 kg sliding over a rough surface. What is the work done by this force in 1 minute? 1 minute. Now here, displacement is not given straight away. In question number 2, displacement was also not given straight away. Initial position was given, final position was given. You found out the displacement. Here the displacement would be found out in a different way. It is moving with a constant velocity of 2 meter per second. Please remember, it is moving with a constant velocity of 2 meter per second. How much will it move in 1 minute? So you can find out the displacement. 2 meter per second multiplied by 1 minute, not by 1 minute, 60 seconds, 2 meter per second multiplied by 60. So the displacement S or delta R will be equal to 120 meters. I hope you got it. 120 meters is the displacement. Force is 5 newtons. Multiply 5 with 120 and you will get the answer as 600 joules. Do we understand this? Can I have some reason that we understand this? Simple question. Displacement was not given straight away. We had to find out the displacement, take the dot product. Here, angle is not given. So we'll assume that the angle is 0. We have assumed it. If the angle was given, it will be F dot delta S. Doesn't matter. You just have to multiply by cos of the angle. I hope now you are mature enough to get this. Now I'll do one more question. Question number 50. And here it comes for you. 50? Question number 5, not 50. A 10 kg satellite. Now again, we have not studied satellite. Does that make any difference? Let us see. A 10 kg satellite completes one revolution around Earth at a height of 100 kilometers in 108 minutes. What is the work done by the gravitational force of Earth in one revolution? We'll assume here that it is moving in a circular path. We'll assume here that it is moving in a circular path. Now, instead of making it one revolution, find the gravitational force of Earth, work done by gravitational force of Earth in half revolution. I just changed the question to half revolution. In half revolution, how much work gravitational force of Earth does on it? Does anyone have any answer for this? A, B, C, D. Anyone has any answer? If anyone has any answer, please let me know. Half revolution may how much work gravitational force will do on this satellite? That is the question. You don't know anything about satellites. The only thing you know that it moves in circular path. If that much information is given, what is the work by gravitational force? What is the answer? Tell me.
Sir?
Yes.
Sir, option A, sir.
Option A, 108 into 10 into 100 joules. What makes you think that, beta? I have made half revolution. Have you seen the question? I've changed the question to half revolution. Not to one revolution. I've changed the question to half revolution. So what is the answer now? So if I make it half revolution, I take this as half and I make it as 54 minutes. 54 minutes has to be changed into seconds. So 54 into 60 multiplied by 100. Are you doing it this way? Now remember, whenever a satellite,
yes, sir.
Whenever a satellite is moving around Earth, it is moving in a circular path. This is my Earth and this is my satellite. It is moving in circular path. Gravitational force between Earth and the satellite. Now you don't know anything about gravitational force, but again, this was a question based on previous knowledge. The gravitational force between Earth and the satellite is the centripetal force. Because of the centripetal force, this satellite is moving around Earth. Now, this centripetal force is always directed towards the center, which is the center of Earth. And the angle between them is 90 degrees. Remember, circular motion. In circular motion, work done by centripetal acceleration is zero. Did we remember it? That is why I told you everything about centripetal acceleration. Here also, gravitational force is the centripetal force. And hence, the work done by this force is going to come as zero. Do we understand this? So the answer is zero, no matter the revolution is 1 or half or 1/4 or 1/8. The answer is obviously zero. That was the only reason I gave you this question. Even though I know that you have not done gravitation, even though I know that you have no idea about centripetal acceleration, but the answer is zero. Do we understand this? Can I have some raise hand that we understand this? Okay, please tell me, I mean, the other sir, I don't remember his name. What is he teaching you? He's not teaching you rotation? Well, what are you doing in the other physics class? Which topic are you doing? Is anyone answering or not?
It's fluid mechanics, sir.
Okay, sorry. I had the idea that you are probably doing a circular motion. Sorry, I had the wrong idea. Anyways, the next heading that we are going to do is this one. Work done by a variable force. Work done by a variable force. Now, how do you find out the work done by a variable force? You already know it. If I have a variable force, the small work done will be F dot dr. The small work done is F dot dr. As simple as that. How do I find out the total work done? How do I find the total work done? I integrate this. I integrate this. When I integrate this, I will get delta W and it will be integral of F dot dr. So I will now write it like this. This is the work done by a variable force. Remember, this is also the work done by a constant force. Only difference is, in case of a constant force, F dot dr becomes F dot delta. So this is the work done by variable force. We'll move ahead with variable force, work done by variable force in the next class. In the next class, we'll be talking about work done by the variable force. I have already given you a small task to do all the 4 or 5 questions that we have discussed once again, and you read this topic, work done by a variable force, from the point where I have ticked it to this point. To it's only this much up till here. So if you can read it up till this point, the one paragraph, if you can read this one paragraph up till here, it will help us a lot in solving the question. This question that we are going to come, if you can read and write up till here, it is nothing. What they have done here is taken the dot product. F is written as 3 components, fxi, fyj, fzk. Delta R is written as dxi, dyj, dzk. Then they have taken the dot product. I dot I will be 1, rest all is 0. J dot j is 1, rest all is 0. K dot k is 1, rest all is 0. So you will have an integral of this type. The work done by this force will be fx dx ka integral from x1 to x2 plus fy dy ka integral from y1 to y2 plus fz dz ka integral from z1 to z2. Can you write this? Do you understand this, how it is achieved? Can you do it on your own? There's some things that you must do on your own. Now, once you do it on your own and understand it, you will never ever forget it. So that is the reason I am giving you this as homework. Can you do it? Can I have some reason that you can do it? Just write this. You should be able to understand it. Work done by a variable force is fx dx ka integral, fy dy ka integral, fz dz ka integral, x1 x2 y1 y2 y2 z1 z2, and that is all that you need to understand. In the next class, we will move ahead and we will write some important notes about work done. We will also discuss why we are writing this as delta W. So we'll write some important notes that is not there in your notes that I will give you. So you have to write it in the next class. The next class will be a very important class. Do not miss it. Right now, we are finishing this class. At this point, if you can do, after writing this question, if you can do these sample problems, that would be icing on the cake. I don't expect that you will do it because you hardly do any homework anytime. It disappoints me, and that is why I have stopped giving you any homework. But still, I'm trying. I keep on trying. That is how I work. So there are some sample problems given on work done by variable force. Problem number 6, problem number 7, up till problem number 9. Only 4 small problems. If you can do these small 4 problems on your own, after reading and writing that part, I'm sure you have understood the entire concept. So it's for you. Self-help service, I call it. Self-help service. And I will be giving you this self-task because that will make you independent. I don't want you to be We call it tigers on paper. That like West Indies ka cricket team, they are tigers on paper. On paper, they are very strong, but when it comes to actual playing, they are all zeros. I don't want you to be becoming like this. I want you to become self-dependent as well, that you can do some task on yourself. And that is the reason I'm giving you this. So I hope that you do this. If you don't do this, I will again do it in the class. But if you do it, I would be pretty happy and you would be happy with your own performance that you have done something on your own. Everything is there with you. You don't need anything else. You just need a bit of confidence and take out a bit of time from your life to solve this. So on that note, I'm going to wind off this class. If you have any doubts, you can come up. Else the class is over from my side. Take care and have a very nice day.